Okay, so today I'm going to tell you about photons, okay? And before I go on to more detail on photons, I need to tell you about the electromagnetic spectrum. So, electromagnetic spectrum is when we're talking about the electromagnetic waves. They are transferred by, for example, so when you have a star is emitting electromagnetic waves, you can have it in other sources. At the moment we are just going to focus now on the spectrum, so I'm just going to tell you about the different wavebands we can have, okay? So we can have, for example, radio waves, microwaves, infrared, visible light, so everything our eyes can detect, and then we can go to the ones with the most energy, so-called ionizing, which is the ultraviolet, X-rays, and gamma rays. So when I was telling you about the 7 different parts of the electromagnetic spectrum, I was telling you in wavelength order, starting from the longer wavelengths, the radio waves, going to the shorter ones, which are the gamma rays. Doing the opposite to the wavelength, we have the frequency, okay? So the waves that have the longest wavelength, like the radio waves, they are the ones that have the lowest frequency. And then the waves that have the shorter wavelength, like gamma rays, they have the highest frequency and energy, okay? So that's why when we talk about the electromagnetic spectrum, we can divide it into visible light. Everything with a frequency above visible light is called an ionizing radiation, so it can form ions, and everything below in terms of energy and frequency, everything that is below the visible light is then called non-ionizing radiation, okay? In terms of the electromagnetic spectrum, there is a table here where you can obviously take notes on what are the wavelength range for the different types of electromagnetic radiation, and there are certain things we can talk about the electromagnetic radiation that we should know already. For example, our eyes can only detect light from the electromagnetic spectrum. Every single object emits infrared radiation unless they are at 0 Kelvin, which is minus 273.15 degrees Celsius. So if something is above 0 Kelvin, then the atoms are vibrating, so it emits heat, okay? In a vacuum, all electromagnetic waves travel at the same speed, and the speed, which we can say is c, so that's the symbol we use for the speed of light or the speed of any electromagnetic waves, is 3.0 times 10 to the power of 8 meters per second. And I can even have the wave equation where I relate the speed of my wave with this figure here, which is going to be the wavelength, so that's the Greek letter, the lambda, times mu, which is going to be standing for frequency. So speed equals the wavelength times the frequency. Wavelength comes in meters, frequency comes in hertz, but because hertz is the same as saying 1 over second, or second minus 1, speed will be in meters per second, or meters second minus 1. More things. So, as I said before, the higher the frequency of a wave, the smaller the wavelength for that wave, okay? And that comes again from the formula. And wavelengths are often expressed in nanometers, and m, where 1 nanometer is equal to 10 to the power of minus 9, okay? So this e is saying that I have to the power of minus 9 times 10 to the power of minus 9. Now, electromagnetic waves, that's when you have an electric wave and a magnetic wave. They are traveling together, okay? And that's how they look like in here, okay? So I have here in red the magnetic wave, in blue here I have the electric wave, and they are traveling together. And when they are traveling together, they, and this is what I'm talking about now, they both travel perpendicular, so in 90 degrees angles, each other and to the direction that the wave is traveling, okay? So they do something like this, okay? At the same time, the magnetic wave is doing the same, okay? So traveling at 90 degrees to the direction, or the oscillations or vibrations are at 90 degrees to the direction that the wave is traveling and transferring energy. So because of that, they are called transverse waves, okay? Because they vibrate or oscillate perpendicular to the motion of the wave or the energy transfer. Second thing we need to know about these electromagnetic waves. These both waves, the electric and the magnetic, they vibrate in phase with each other, okay? So they both reach a peak together. So here we go, both in a peak together, both in the middle together, so they are in phase. Now, photons. So when you have electromagnetic waves, they are emitted whenever there is a charged particle that loses energy. And for example, this can happen when you have a fast-moving electron that is stopped or slowed down or changes direction. So again, you release a photon. Or when you have an electron in a shell of an atom that moves to another shell, higher or lower. Sorry, actually it should be just lower, because if it goes to a higher shell, it actually needs to absorb a photon. I'll go there later on. So to say this part again, so you can get a photon being emitted when a charged particle loses energy. It could be a fast-moving electron that is stopped, slowed down, or changes direction. Or it could be an electron in a shell of an atom that moves to another shell with a lower energy level. If it happens to go to a higher energy level, then it needs energy to do so, so it actually absorbs a photon because it needs to absorb energy. Electromagnetic waves, they come in packets or quantum, okay? And we call these photons. So it's kind of you having lots of boxes, and all of them, each of them bring a little bit of energy, and then all of them traveling together. That's what makes the electromagnetic waves. Now, if I want to calculate the photon energy, I can use the formula that is showing now here on the PowerPoint. So E stands for the energy of the photon and comes in J joules, okay? That's equal to H, standing for the Planck's constant, which is always the same number, so 6.63 times 10 to the power of minus 34 joules second, so that's the units for the Planck's constant, times F, where F stands for the frequency, okay, which comes in hertz, or as you know, second minus 1. So again, if you look at the units, you have joules second times second minus 1, so the second and the second minus 1, they cancel each other out, and you get the units of joules for the energy. Just for us to train this formula, I have here an example. So it says calculate the frequency and the energy of a photon of wavelength 590 nanometers nm. So if you want to know the frequency, you can use the wave formula, okay? So the wave equation. So the wave equation says that c, the speed of the wave, is equal to the wavelength times the frequency. Therefore, the frequency equals to the speed divided by the wavelength. So I'm going to have 3 times 10 to the power of 8, which is the speed that I have for an electromagnetic wave, divided by 590, and then I need to get the nanometers into meters. So I do 590 times 10 to the power of minus 9, because 1 nanometer is 10 to the power of minus 9 meters. If I do so, I get 5.08 times 10 to the power of 14 hertz, okay? So again, always say the units, always say how you do the calculation, so you can get full marks in an exam. Finally, the second question was about the energy. So for the energy, I can now use this formula, because I have the Planck's constant, is always a constant, and I just calculated frequency. So energy equals HF, where H is always the same number, so 6.63 times 10 to the power of minus 34, and then times the frequency that I got in the previous exercise, so 5.08 times 10 to the power of 14. If I do so, I get 3.37 times, sorry, it's now on this side, 10 to the power of minus 19 J joules, okay? So that's on the photons and the formulas, all these things so far. But now I'm going to tell you about one more thing, which is the lasers, okay? So I'm going to tell you about laser power, where you can apply the photons to the real life as well. So first of all, if I'm talking about a laser beam, I'm talking about photons that all have the same frequency, okay? And if I want to know the power of a laser beam, I have a formula. And when I talk about the power of a laser beam, I mean the energy per second that is transferred by the photons. So because it's energy per second, the units for power of a beam is going to be joules second minus 1, or joules per second, okay? And the formula to get the power of my beam is going to be equal to N, where N is the number of photons in the beam that are passing a fixed point every second, times H, the Planck's constant, times F, the frequency, okay? So that's all for photons and lasers, and then later on we are going to apply more of this stuff to particle physics. See you later!